Thank you for coming and attending our inaugural IS Distinguished Fellow lecture. So today we are very honored to have Professor Prof Teck-Peng, okay, who is our IS Distinguished Fellow and a very world-renowned chemist, organic chemist. Okay, and he's also the Distinguished University Professor at the School of Chemistry, Chemical Engineering and Biotechnology. Professor Loh was the founding head of division, okay, at the Chemistry and Biological Chemistry at NTU. So Prof Loh's research focuses on making the manufacturing processes more green. So in all the manufacturing processes, you will need to use organic solvents, and organic solvents, we know, tend to be toxic, flammable, and this is actually not so good for the environment. So Prof Loh is a pioneer in actually making all these processes very green. Okay, so Prof Loh won a number of awards. So he received the prestigious President Science Award in 2018 for outstanding research accomplishments, okay, in advancing organic chemistry and green chemistry. And he also received the Best Researcher Awards from both NUS and NTU, the GSK SNIC Award in Organic Chemistry, and the Chinese 1000 Talent Award, as well as the Japan Yoshida Prize. So Prof Loh is an elected Fellow of the Academy of Sciences in Singapore and Malaysia, and is also the Associate Editor of the Journal of Organic Chemistry and the Green and Sustainable Chemistry. Prof Loh is also a member of the advisory boards of international journals such as Chemical Communications, Chemical Record, and the Asian Journal of Organic Chemistry. So, without further ado, let us put our hands together to welcome Prof Loh, and we'll listen to his exciting talk on this green and biocompatible reactions from discovery to applications. Thank you.
Thank you, Mr. Sam, for a very kind introduction, and also for inviting me to give this talk. This is my second time actually talking at IS. I've been away for all in all, so I'm not interacting with many of the students. Nice to be back and try to give a presentation on some of the things that we've been doing for the past almost 13 years, all the way how we move organic chemistry to the present day research in my group. I think I probably need to start changing it first. Okay. So when I came back in 1994, like all the young...
Sorry, I think there's a lot of feedback.
Yeah. Okay, so when I came back in 1994 after my PhD in the US, I think like all the young professors, you start to think about what you want to do as a researcher and how you get your tenure. Okay, so there are two things is balance again. So I was looking and thinking what is the project that I want to start in Singapore. I think many people didn't know that current Singapore environment is really a third world country environment. I think we don't know that. Most people don't know. Okay, working outside the film hood, under a very hot atmosphere, no aircon on the bench, with only high school students, even using secretary to do the first research project. So I think we have grown very fast from the third world to the first class right now, infrastructures, and we changed our systems of recruitment. We've got the best people from the world right now. So things have changed very fast from 1994. And because things have changed, the way we approach research also changed. When I teach organic chemistry, I teach electrosynthetic analysis, I always tell students that when you try to make a molecule, if you want to make a molecule in Singapore in the old days, you only have one knife, okay? They're fighting with you. You need to climb up yourself, the coconut tree, and pick up the coconut yourself. If you come from a very advanced country, you use a machine gun, you just pick it up, okay? So the strategy changes throughout the years when you do research. When we have money, we have students, things change. And because right now I think we are in a situation where we are more like an advanced country, now we can do research without thinking about just the money, but more on the innovation and the application. So you can see that when I first came back, I actually organized out the Nobel Prize winners in organic chemistry and see what are the things that I can do. So you look at it in the 1960s, for example, people focus on the new concepts and strategy. For example, you know, the Uber and Corey, my former supervisor is Corey, he came up with the concept of electrosynthetic analysis. So he changed the way molecules were made. In the old days, when you make molecules, you try and error. You fail, you do it again, you try it again, okay? That was the old strategy. So Corey came by and said, no, let's come up with a more systematic approach using electrosynthetic analysis. It's like the clothes right now you're wearing. You identify the collar as one pattern, the collar as one pattern, sleeve as another pattern. So you identify a pattern and you know how to cut the molecule backward. Then all these people also use the biosynthetic approach, count the body. But the college graduate now you have two approaches. So the concept that changed the way we make molecules. Hugo is the genius, he came up with molecule. Without even NMR, we were able to make complex molecules in the old days. Okay? And then after that, people start to think about come up with methods, practical methods to make molecules in large scales, without thinking about greenhouse, without thinking about environment, not saying without thinking. You were having difficulty thinking to solve this problem. So they make at low cost. That was their main focus. Okay? So you can see that these are many of the Nobel Prize winners who work in this area. So at that time in the 1990s, when I first came back, there was very little focus on green chemistry extract. But the thing will come, I know. I cannot share this one. So, see, that's actually, so I have to say, okay, wait, okay. So, at that time, I think my thinking was that green chemistry will come soon. It's like when you get richer, people start to look at green chemistry aspect. So what we wanted to do is that come up with new chemistry, with hopefully useful chemistry, and then must be green and practical. That was our ultimate goal of doing organic chemistry. I think organic synthesis contributed a lot to the pharmaceutical industry. We made a lot of new drugs, we construct new molecules. That's actually our power, making molecules. So when you look at the way all these, the organic chemistry was done, is that they were done using organic flavor, organic solvents, and that always caused fires, explosions. So can we do the reactions in water? That was the first question I asked when I came back to Singapore. People do the reactions under acidic and basic condition. Can you do a neutral condition, like our biological system? Can you do it to functionalize protein, okay, without destroying the protein? A reaction will die at high temperature. If the reaction doesn't go, your boss will tell you, do the reaction, keep it up, okay? If it still doesn't go, then you just add things inside there, deuterium activator, deuterium catalyst, you heat it out, okay? And then there will always problem with selectivity. They give you a mixture of compound. Okay? Can you do the reaction with 100% selectivity, green, atom economy, no waste. Okay? So the dream process is that do the reactions, okay? Get atom economy reaction, no waste. Do it mild temperature, room temperature, okay? No waste. If possible, don't use organic solvent. So, in the past 2 years, my research changed a bit. So, in the very beginning, I tried to come up with a toolbox of green synthetic methods. That was the ultimate goal, and tried to make molecule in a green manner. But in the past few years, I switched my directions, more on the use-based inspired out research. And these are more difficult in the sense that we actually look at solving a big problem, for example, in biologics or in materials, and then try to come up with new technology, innovation to solve those problems. This one requires reading article, not just in organic chemistry, you need to read in material science, you read in biology, drugs, in different areas of the science. It's better? Yeah? Okay, so in last 5 years ago, I started to move away from just doing new methods, green methods. I tried to go the other way around. That means come up with a problem and try to find a new innovation or new technology to solve this problem. For example, the one we focus a lot is on these drugs here, biologics, protein type biologics. Can you actually get new technology to come up with new protein-based drugs? To do protein-based drug, you require the reaction to be done at a very mild reaction condition. I think most people know, if you do protein functionalization, you cannot heat it up, you destroy a three-dimensional structure. The three-dimensional structure is related to the function of the protein. You cannot use matter. Many times the matter also destroys the three-dimensional structure of the protein. You require a very mild method to do protein functionalization. So the protein functionalization actually serves as a guide for us. So sometimes the simulated reaction is dreamed of. Okay, so this is a big topic. We also do isotope labeling of drugs to get fast drugs access. We also try to design target covalent inhibitors. This is a drug research we're working right now. On the material side that we just started, I've been studying material science for the past almost 8 to 9 years. So the project just started not long. We try to design a 2D to 3D materials using external stimuli. For example, like form it, see whether you can get a paper to fall into 3D structure. like the origami, the chocolate, different structures. We started this project not long ago. Circular economy, can we put something into the polymer, and then you break it apart easily, recycle it to the monomer, and get back again to recycle it. And this is a hot topic right now in Singapore, the circular economy. We're working on this area. Cell healing compound, can we design the reactions that can do cross reactions, okay? And then you will get cell healing, cut the materials and then heal back the skin. You can do that. So we just started all this new project along. In the areas of food chemistry, we also do like how to convert UV light to red light using a biocompound or plastic or glass. So that when UV light go through that, you increase it to get more red light that's required for photosynthesis to speed up the growth of plant. So that's one area we started. Can we change the rice straws? Okay, we collect the rice straw, convert the rice straw into platform chemicals to make new drugs. Okay, and then the other one is artificial meat. You do cross-linking or protein to get artificial. This is another hot topic in the food industry. So these are things that we have been doing right now. Again, carbon dioxide capturing, just not just capture and make into peptide. We just started this project in my group here in Singapore. How do you do that? It's challenging, not easy, I say that, you do that. So these are actually more like use-based basic research. Okay, so the other way around rather than the fun side here. So so where do you get the inspiration for green reactions? The best way to get the inspiration is our own body. Our body actually do very green and clean methods. Okay? You cannot make toxic compound in the body. You'll kill yourself. Okay? So our reaction uses water. Our body never use organic solvent. They use water as a solvent to do organic transformation. So you can see that our reactions are done in water. It must be in neutral conditions. Enzyme as a catalyst. Okay? Very rarely you use metal. Because some metal but not metal. Try to be metal-free. And then the reaction usually are very fast and very selective. Enzymatic reactions are very fast, selective, and very dilute. Okay? Use non-toxic chemicals and no purification required in our body because you pick up the compound and use it for the function. But in organic chemistry, sometimes it's different. You need to purify the compound and use it for subsequent steps. These are more challenging. So our body system carry out reactions that are very efficient and very clean. For example, this reaction here is an aldol reaction. It's catalyzed by this enzyme called aldolase. This aldolase catalyzes a very efficient aldol reactions to give a single product. This reaction actually involved an amine catalyst that was awarded a Nobel Prize about 2 years ago, which used organocatalyst. The organocatalyst actually uses the same activation mode of this aldolase catalyst. Okay? And this is another reaction in the body, in the biological system, converting methane to methanol. Up to now, there's no reaction outside the biological system that can actually mimic this process. Very challenging. Another process here, which involves polyene cyclization, from a very simple precursor, you get into a very complex steric structure. This was very challenging. Up to now, there's not really a real meaning of this system outside the biological system. It sometimes involves a chair type transition state, but the our body also involves, sometimes uses a chair transition state, which is very difficult. And we have been trying to do that, but up to now, there's no example of having a chain transition state of reactions. So our biological system provides many examples, many inspiration for us to come up with the reactions that can mimic this process. So in our lab, one of the programs in my group is to come up with this type of process that can mimic the biological process, and sometimes even come up with better processes than the biological system. So we started off with polyene cyclizations in the 1990s. Actually, it was done by high school students, Olympic medalists. Actually, now he's a professor in NUS, Susin, started this process. Okay, so he went on to Harvard to a PhD, and now he's a professor. That's called tenure in the US. Okay, so he started this process, these reactions. We tried to do a polyene cyclization and mimic this process. Very tough reactions. So the student, I won't go through the detail. So when we do the first reaction, the reactions, the TLC have many so many stops. One stick. Okay. So finally we cut off the salt and analyze the product, then we zoom in the condition screening, and finally come up with one single product. We actually finally got a system that works that can mimic this biological process. This biological process is very powerful. You can see this enzyme constructing a single molecule, this foreign structure in one single steps, 8 stereogenic center, 1 out of 128 possible isomer. Very powerful reaction, okay? And then highly substituted compound is formed. Okay? And these are done in water, neutral conditions, matter-free, fast reactions, highly selective, no toxic chemicals involved. So in my group, actually, we try to mimic this process. So we actually used a different type of initiator. At that time, we used the Lewis acid method in organic solvent, not in water. I started off. And we're able to actually come up with this type of polyimide cyclation. It works well. The intermediate involved is the oxo-carbon ion. I won't go through the detail, okay? And then later on, we're able to do a little bit of water. Too much water also cannot. The yield is very low, okay? And they also work on this one using a chiral complex to do chiral asymmetric polyimide cyclization reactions using this type of scandium chiropyrox catalyst. And then we use this one to make complex molecules. So for so many years until now, we have one challenge, we still have a lot of problems to solve. First of all, we're not able to do the reaction in pure water. It was very challenging. Only recently, we found that we have not just found that oxo-carbon ion, I didn't draw the structure, still the paper is there, we're still writing the paper. It's a stable oxo-carbon ion that's stable in water. It 2 cc more in water, we just discovered it after so many years. From 1990s until now, finally we see the light that we can do the reactions in water, cleanly for this type of polyimide cyclation reaction. Another reactions that are very interesting is to mimic the amino acid amino mutase reaction here. This is a special enzyme. They can actually affect amino group migration reactions from the alpha amino acid to the beta amino acid, or the beta amino acid to the alpha amino acid, using this enzyme called mutase. Okay, so this amino mutase is a very powerful enzyme. Unfortunately, up to now, it's very difficult to do outside the biological system. You can do it, but the mixtures of the alpha and beta amino acid is very difficult to separate. Very, very difficult. We spend the cost of separating this alpha and beta is sometimes so expensive that people don't want to do it. Okay? So can you mimic this process outside the biological system? So if you can mimic this process, maybe we can even big enzyme. We not just do 1-2 amino group migration. Maybe we can design a 1-3, 1-4, or 1-5 amino group. The enzyme cannot do. So you can do better than the enzyme. Okay? So this is what we, or you can do a ring expansion from a 5-membrane to a 6-membrane or 7-membrane. Can you do that? Okay? So this was the challenge that I gave to one of the students. To cut the story short here, I won't go to the mechanism. This is the biological system. We involve a radical intermediate, CH activation. Okay? They undergo this ring. Finally, this exuding ring carbon radical, which will open, they effect this migration of nitrogen from this carbon to the other carbon. So this is a radical process, okay? So what we do is that we draw out the mechanism on the paper, we design it, we try to convince the student to take out the project. It's very tough, because it's a very tough project. But I know that this project has gold inside it, so that's the way we do it. Sometimes very mean to students, okay? We know something is there. So just play with one amine group here, throwing oxidants, okay, one electron oxidants, and then do the reactions. And very luckily, sometimes very luckily, okay? In the presence of methanol, we're able to effect the amino group migration reactions from this carbon to this carbon. Let me again cut it short. So what happens is that we're able to affect this carbon, this nitrogen from the blue carbon to a red carbon, in this case here. It's not exactly the same as the biological system, but similar. You can see that after this carbon migrated from the blue to the red carbon, we get the amino acid count. This actually comes from the methanol solid that we put in. The mechanism is a bit complex. Later on, you'll see the complex the mechanism. We go through a series of experimentation to come up with this mechanistic proposal. So what happens is that these reactions involve the formations of this imine plus and then an enamine. And undergo one electron oxidation, and finally got this intermediate, which is very important. This intermediate was formed, and this oxygen lone pair from the methanol, the toxic group here, actually facilitated the ring opening that effect the migration of the nitrogen from one carbon to the other carbon. So it actually was a try and error project. We just threw in, and then we got the product. Then we came back on the mechanism. And from the mechanism, right now we think we can design a new reactions. If you throw in an aldehyde and an amine as a control experiment to make this enamine, not from the amine but from the aldehyde and the amine, we also got the desired product. And now we discover a new reactions to do alpha amination of the aldehyde. So indeed, by using this copper catalyst at the beginning here, and then with the oxygen as well oxidants, we're able to effect this enamine to this amino acetate. And now we can use just directly amine and aldehyde to do this alpha amination. So for mechanistic study, we're understanding the intermediate, and now we can design another process, okay, and involve alpha amination of the aldehyde. Not only that, then we ask ourselves, can we replace copper with non-metal? So I'm not interested in metal. I always want to go with this. I'm sorry for those doing inorganic chemistry. Okay, so I'm trying to. I do a lot of metal, okay, but I always try to go away from metal. So in this case, when we found that we use aluminum as the oxide, we replace copper and just oxygen here, we're able to do the same reactions, alpha amination aldehyde, to get this alpha amino acetate compound here. Whether we use this use the product aldehyde, we can insert amino group here, we get this one here. You can even insert amino group here. This one you can bind, citronella, you can insert amino here. This is the Claisen rearranged product, you also can insert amino compound. This is the steroidal aldehyde, you cannot insert amino here. So it's a very powerful method, very simple, no method, mostly about room temperature, you can do this reaction. Okay? So after getting the product here, this amino acetate, this is the amino acetate here. Okay, this is our product. From this reaction, very simple, we get the amino acetate, and then through a few steps, we are able to make this complex molecule. Again, I won't go through the detail. So it's a very powerful method to get to the synthetic building block, and finally construct our products. Same thing here. We have also made this molecule, and this molecule using this very simple reactions with just iodine and methanol with oxygen as oxidants. Recently, we are challenging to make this molecule a very hard molecule, complex molecules, and actually Jocelyn is here, she's trying to struggle to make this molecule. Our goal before I retire, hopefully, is to do a complex molecule in 20 steps in one pot manner. If the reaction is done using no matter, no waves, you add A to B together. Then after the reaction done, you take C, to D, to E, to F, and after all the reactions done, you recrystallize it in water. That was my dream, okay? And then no organic solvent, no matter, one pot multi-step synthesis. That's the dream process. It's not easy. We have 3 people working in this project right now. 2 collaborators living in China and 1 Jocelyn here working in this project. Another thing that we just discovered very recently is still, we just dropped in the manuscript. From the reaction mechanism, I won't go through detail because it's not published yet. Now using the mechanistic detail that we studied from the amino group migration reactions, now we can actually do an amine addition to the 1,3 alpha beta isocarbonyl compound. I think if you study organic chemistry, you know that it's very easy to do 1,4, okay, because it's electrophilic. Very difficult to do 1,3. But we're using our methods, we have a simple method, a method of reactions. Now we can do 1,3 addition reactions to the alpha beta isocarbonyl compound. Okay, now come back to the water-based reactions. So when we started water-based reactions, we put them into 3 categories. The first category involves a water-tolerant organometallic, like Grignard reagent. We know that Grignard reagents are not stable in water. We cannot touch water. Can we design an equivalent of Grignard reagent that's stable in water? Grignard reagent is the Nobel Prize winning reactions. It's very popular because you can react many different electrophores and very easy to make it. You just use the organohalides with sp2, sp3, sp, you put a magnesium, insert into that, you change from carbon electrophilic to the C- type of carbon. Very powerful. And that's why, can we design a water-tolerant organometallic? Can we bring that? That was the first question we asked. Next thing is that can we design a catalyst that's stable in water like enzyme? Even it's a metal complex, can we design a metal complex that's stable in water? Or you can also use organocatalysts that's stable in water. So we started this project in 1992 on organocatalysts. We used up badly to the people that work in this area, okay? So we were very small at that time. And then lastly, can you do reaction without catalysts? No catalysts, just add them together. Now these are very scary because there are a lot of reports that get fake result. Because sometimes your glassware is not clean, there's some metal inside that transfer, can also catalyze reaction. Sometimes you have also the starting material has trace of metal, they can also catalyze the reactions. So for catalyst-free reaction, you have to be very careful to make sure that this result is truly work without a catalyst. So we wanted to do reactions, so we started to do water-based reactions, focusing on water as organic solid. There are many questions at that time people asked when we submit the publication. Prof Loh, you use water, but after the reaction you extract the organic solvent. Now you do column chromatography with organic solvent. it causes problem with disposal of the waste, water waste. So this is a question that we continue getting and try to refine it. So hopefully at the end of the lecture, I can show you some reaction that we don't even touch organic solvent. All the way to the end, after the reaction in water, the compound crush up in water and just filter it with a compound. Okay? No water, no organic solvent, just pure water. So we know many organometallics are not stable in water. This is very challenging. So when as a student, we always tell myself to flame dry the flask, don't touch water, very careful. You know? Suddenly when I came back to Singapore, I said, water-based reactions. It's scary. I saw a paper, okay? I saw a paper that said that you can do water-based reaction with an organo-greener reagent. And I was very lucky because I was so poor in NUS. I go to the chemical store to search for a chemical that the old professor threw away. And I found a bottle of indium powder. A big bottle of indium powder. And I found that indium, there was a report by another group saying that indium or not indium, you know, in water. So it's something lucky, you know, you go around searching and then you have no money, you go around digging. I was preparing O3 evaporator from the professor to throw away. And I found this bottle of indium powder. So we started to do indium chemistry. Okay, so greener, not stable, like very powerful, not stable. This was given this Nobel Prize in 1912. Okay, very powerful reactions. So can we replace with a different metal? The metals can work, that work in water. We are not discovered of this thing, okay? We have done it with tin, zinc, and indium. We can work in water. Okay? So we study a lot. I tried to, because the discovery had really done organoidium in water. So when we try to go into this area, no matter what you do, we are giving credit to the discoverer. And after a few hours, I find that it's better go away from this area. Go to my own area. No matter what you do, although we discover new method to make organoidium, alkyl indium. Okay? We also make new indium. We do a lot of stereochemistry study, we control stereochemistry. We do even substrate scope. We use it to make complex molecules. But I think I have to stop because whatever we do, we are contributing to the guy. Okay? It's like organocatalyst. You don't want to do it contribute to another guy. But when you're poor, no choice, that's okay. Okay? Whatever you do, you just help him to get a Nobel Prize. Not moving. So go to a new area. so that we actually read chemical review in 2013, cover about 800 to 900 publications. I just wrote another two review, chemical review, one chemical review. It took me about 3 years to write chemical review, almost exhausted because of COVID-19. I thought it was very easy. Then I realized everybody writing review because nobody do experiment. So the whole world is writing review and become very competitive to submit a review. In the old days, nobody submit review. I usually don't write review. I think it's a waste of time. But COVID-19, I wrote like maybe 4 review articles. Okay? So this is the first part. I won't go through this, I just summarize the detail. And then the second part was actually very interesting, is that we discovered a metal complex that worked in water by chance. Something we got lucky. And something you're lucky and the student lucky, then you give more and more difficult project. Wow, the student can solve. Then until one day, student commit suicide. Very dangerous. So they can tell themselves, bring down the project. Okay? Because like Corey, his project is going more and more difficult. Okay? Because one student solve it, wow. More difficult one. And then you come in at the end of his retirement, okay? He give the most difficult project that he cannot solve for 30 years. And he expect you to solve it, okay? Sometimes you have to go back to the scene. Then you gotta be careful, okay? Don't give too difficult projects to students. So we discovered the indium complex. So we wanted to replace organoindium to make sure it's catalytic. Because indium is expensive. So we tried to do transmetallation. So we use zinc and indium trichloride or tin indium trichloride, and it works very well. Then after it works very well, we asked the question, if indium trichloride can use to transmetallate this metal in water, why not use this one as a catalyst in water? So I checked the Merck index. And now students don't use Merck index anymore. Okay, I checked the index. Indium complex stable in water. So I decided to use this indium complex to do many reactions in water. That's how I get my camera. Indium complex, this method. So you publish CC4, CX, all in water using this complex, okay? And it's very tough, I can tell you, because when you go to a new area, not your professor's area, you are competing with the group in the world. And once you publish a paper and say that yours is better than his, some people cannot take it. He'll come after you and make your life very miserable. I won't tell you about the people here that when you're competing, they make my life very miserable. Okay? So sometimes people are not. So that's why in Singapore, we want people to do research away from the professor. Why? To make sure that you can actually stand the pressure You can compete with the world. The enemy can fight you, you fight back. And after you survive, you're strong. If you don't survive, you die peacefully. Okay? And that's the way US do it, the same thing. You cannot do project related to your professors. You cannot touch your postdocs work, cannot touch your why? If you touch your postdoc work in your professors, supervisors work, PhD work, sometimes you submit a paper. You know two referee already. One your postdoc supervisor, one your PhD supervisor, and the last referee reject, two okay, you still get in. That's not fair. So I tell students right now, when you do research, you make sure the paper has three important things in the paper. Whoever become your referee, look at one thing is, and then the other two things okay, but he still say go through. Then the other professor look at it, wow, there's one thing that I like. But your paper only have one thing inside there, and two of them don't like it. And you don't have people to support you. Very difficult to go through. All these my papers already one thing hard. Now I encourage you, when you do research, your paper must have two or three things. I always tell people this story, is that you're watching this joke thing. I like to watch the joke thing. What's the best joke? When you have three things, it make you laugh. Then pause for it, make you laugh again. It make you laugh again. Oh, these are the best joke. Don't you think so? It's a paper. You look at the key point, wow, open eyes. Then you try again, wow. Then you finish already, another one. Oh, these are the best paper. But difficult, it's not easy. so I guide people with red paper, look at three key points, then you see three types of referees that can look at the paper and all get excited about your paper. Then I'll say these are the good paper, okay? So we also do other catalysts. Actually, this is done by Professor Chia collaboration here. He's here. We actually come up with other boron catalysts or ion pair catalysts work in water. Okay? But then more recently, we have interesting catalysts using this boron catalyst. Okay? And this boron can grow a crystal after this water complex. And the good thing about this interesting is that this catalyst require only about 0.5 mole%, 1 mole% of the catalyst. Why? If you do catalytic reactions with metal or non-metal catalyst, your substrate bind to the catalyst, and after reaction come out. When you need to bind and come out, it's very difficult to get catalytic loading of less than 0.5 mole%. Very difficult. So this is on the surface. So this hydrogen network that's produced here actually catalyzes reaction. The substrate in the product doesn't touch the metal. And this concept actually was done by Mallory many years back as a student. Million cycle. I was very impressed when I listened to his talk. Okay, to get million cycle, the substrate in the product doesn't bind to the catalyst. It's on the surface. Okay. We also do organocatalysts. It took us about 15 years to make this. You take this catalyst. I designed when I was a student. Okay? I wanted to make this organocatalyst a U-shaped and an S-shaped organocatalyst. We actually spent like 4 or 5 students before we make it. We keep failing. Okay? Finally, we make it. We make it 2010. An interesting project become after it become a very outdated project. We made this catalyst to work in water. And very good enhancer activity. And very smooth. So sometimes our speed doesn't match up with the speed in the world. But now I think we are better in this environment. We have good lab and good facilities. We spend a lot of money setting up the central instrument. Why? It's for you guys actually. The chemistry part is actually we all designed the central instrument. Very few universities in the world that the professor or the administrator spend time on basic infrastructure. We want to make sure that all our young professors can get this infrastructure and move very fast. Okay? We also use clay to do organic reactions in water. You can put the clay in the cloth, and then recycle the tea bag. The catalyst in the tea bag. The product comes out, then the tea bag, throw away or use it again. So, and this is not science, this is technological thing. Okay? I think the last part to me will be the most interesting. Catalyst-free, no catalyst reactions. Why? Because using this I moved to protein science. So I slowly moved from just organic to protein chemistry. So we started protein chemistry many years back. When I first came here, but we're scared to go into a new area. So when you're doing in your own territory, you go to a new territory, you're so scared. Because I've never touched protein. I'm a chemical engineer by training. And then my PhD, I can do organic chemistry. Okay, I only studied organic chemistry 1 semester. Biochemistry 0. I went to Harvard, did a biochemistry course. Halfway through, I quit. I cannot follow the course. I kept the book. The book was good. It was by Harvard Medical School. It's a very, very good book. So because bio is very different from organic chemistry, a lot of maybe like this, okay, no. All they can use is either yes or no. Don't get it, see? So it took me a while, because I went for sabbatical in Columbia Medical School. Started to learn protein. My friend was there as a professor. I learned from him. Very luckily again, so I got a student from Novartis. Yeah, seems good. Let's join supervisor student. Use your facilities. So Thomas Geller was at the time in Novartis. So he collaborated with this student who actually came from US. His husband moved here and was actually involved in biochemistry. So he started to look into protein functionalization. So he changes myoglobin, this amine group here, into this aldehyde using a biological system. This is a well method done by Francis. So we did this one to make the aldehyde, and then we do the in-game elevation reactions. Okay? It works well, not bad. When we measure the CD spectrum, we found that the three-dimensional structure of the protein has been partially destroyed, telling us that matter is not good for protein. It can be some special cases, but it's not you want to get a general case, it's better not to have matter. So that actually tells us that try not to have matter if you do protein functionalization. So indeed, just cut this one slide here. Actually, in the 2000, we discovered reactions of gamma-alpha reactions, which actually works without a catalyst, just in water. So I thought it was interesting, and I just published it to try it. And then it came back and said, maybe we can use it for these protein reactions. Indeed, it worked with no catalyst. So I prepare a 5-hour here to get the CC1 formations. So this is the first time we moved into protein, we were able to solve it using a catalyst-free reactions. And we keep the three-dimensional structure. It was not destroyed. It's just very modern. So the next thing we asked is that we wanted to have a toolbox of catalyst-free reaction. Toolbox. To get a toolbox, how do you design a catalyst-free reaction? A lot of people ask me that question. It's very easy. You have a very strong electrophile, very strong. Then your nucleophile must be stable in water. Put water pH+. You find those stable on, and you just throw them together. And if you're lucky, you got CC1, CH1, okay, or CN1, CO1. So this is how we design it. Okay? This is actually from a rough abstract of my review article that I wrote recently. So you got a water stable nucleophile. You got a very reactive electrophile. If you're lucky, you can get a CX1 to form. If you can do these type of reactions with no catalyst, as I mentioned to you, you get very green synthesis of pharmaceutical. No waste. Okay? Atom economy. So extremely clean reactions. You can do multi-step one-pot reaction that I mentioned to you. 20-step one-pot. Because there's no waste, no matter, everything very clean. Okay? Or you can do chemoenzymatic. What does it mean? You do a reactions organic and then you throw enzyme. This enzyme you do water or buffer. Okay? You do combinations of organic chemistry enzymatic reaction. And then finally, protein functionalization or modifications. So let me show you one example where we do reactions where the reaction doesn't touch any organic solvent, no organic solvent, no matter. So we're interested in these type of molecules because they are present as anti-cancer agents in many cases here. So what we do is that we actually reacted an activated allylic alcohol and then throw in sulfuric acid. And very luckily, these reactions actually sharpness make it very hot, and then we usually do a catalyst matter-free system. This publication is in JOC, no? I'm associate editor as well. The JOC paper won him the Nobel Prize. So it doesn't have to be science paper or initial paper or text paper. Sometimes JOC paper is not bad, huh? But then you get a professor in China, you pass on JOC. So what we want to do is that rather than introduce an enzyme or a alkyl group to the protein, why not you react with the functional group on the protein directly? Okay, but there's so many different native amino acid groups on the protein. You got lysine, you got cysteine, so you got N, you get O, you get phenolic. So can you selectively only react with one of the functional group to conjugate with the protein? So usually people choose cysteine, thiol, because they are rare type of amino acid. What happens is that when you want to conjugate, you want to bring important drug molecule into the protein, conjugate together. These are expensive. You want to conjugate to many different functional groups. So you usually selectively choose the thiol group. So can you design a reaction that work only with the thiol group without touching all the functional group in the protein, and done it in water, catalyst free, room temperature, neutral pH. These are always very challenging. So again sometimes a lot of luck, you know. Discovered by chance, sometimes the reaction looks more beautiful than design. Okay, so our student actually worked at this project, and he was very lucky. Actually, I designed a different reaction for him to do. He said, Prof Loh, I don't get the product. And he found that the substrate react with the protein directly. He found that this allylic amide react with only the Thai group here. Conjugation, without touching the other functional group. And the fantastic thing is that this reaction here works in 10 to 20 minutes. Remember, in biology business, it's very dilute. Fast reaction is very critical, very selective. And then we can actually work on, we can bring in different color dyes. We also can introduce it into protein. So why do you want to do protein-based conjugation? It's right now there's a hot drug called antibody drug conjugate, very hot, okay? In China, in the world, okay? So when we started this project about 10 years ago, very few people worked on this project. So when we published the paper on the allylic amide bioconjugation paper in Nanyang Technological, the company wrote to me, want to buy my technology. And I seem surprised, who want to buy my technology? Very people buy my technology. This is too basic again. So I checked the company, and the company is working on antibody drug conjugate. So I want to buy that 30,000 for very little money, so I said forget about it. So I decided to read antibody drug conjugate. And Singapore things like YouTube. Every day watch YouTube first. Watch 2 minute YouTube first. Then you watch 10 minute YouTube. Then you watch 1 hour YouTube. If you watch 1 hour YouTube first, you can understand anything. The 2 minute one usually is from company. They are very precise, very clear, and very easy to understand. So I encourage you, when you enter an area, you just look at go and find those YouTube like 2 or 3 minutes first. Company type, very clear and very concise. Then slowly you watch those like 20 minutes, 30 minutes, 1 hour YouTube. Then you start to become an expert. So why antibody drug conjugate is so popular? So actually this antibody is a delivery system. Depending on the antibody that you can use, you can deliver drug to different cancer cells. You can go to ovarian cancer cell with this antibody. You can go to breast cancer cell with this. Just like a warhead, you bring it there. And then after you bring that, there's a linker here that link the payload. The payload can be a toxin, very powerful toxin drug. They go into the cancer cell, it got released in the cancer cell, boom, and destroy the cancer cell. Very hot. And now they already got 17 FDA approved. When we started, the time was like 4 FDA approved, now it's 17. Why is it so easy to get this type of ADC new drug in small molecule? Because if you change the linker here, change here, this part here, it becomes a new biologics, new drugs. Not like small molecules. Molecules are well protected by the patent. They are very good at protecting the very difficult to go in. Because I worked on small molecule when I was a student. Okay? And my first project in Harvard was actually HIV protease inhibitor. We used to the company back in same design. Okay? Yeah, HIV protease. So I was a secret project. Worked for a few months and we used to the company. But it's same design. The way we design is to stop the replications of the virus. So this one is easier. If you can come up with this conjugation technology here, this is a blue color one. In the linker here, there are other fragments. Fragments that prevent the two things from aggregation. Because when two organic compounds work together, they don't aggregate. So they won't be good. So if there's something that can prevent aggregation, you have a part that can release when after the cat enter the cancer cell. Okay? So you have to have different fragments inside here. This is called the linker. So the linker has two conjugation sites. One they conjugate to the protein, in this case it's antibody. The other one conjugate to the payload, can be a drug, can be other things. And then there are different fragments, release fragment, solubilizing fragments, and different type of fragments. So the whole thing is called linker. Okay? So we are interested in this thing here. So after you enter, let's say we bring a functional cargo, if a drug will become an antibody drug conjugate, it destroys the cancer cell. If you bring in antigen, go into the tissue, it becomes a vaccine. It causes a reaction. Immune response, it becomes a vaccine. And there's an FDA-approved vaccine for this bacteria. And then if you bring in siRNA drug, it can actually switch away the gene, stop the gene from producing abnormal protein. You can cure those, what we call genetic diseases. You cannot cure, just stop it. Then take it, stop it, close it, okay? So these are new things, these are FDA-approved. And very hot topic right now. Okay, so we are right now involved a lot in this thing here. And this thing very difficult to publish paper. And it's all about patent, okay? So this is just how we actually wrote a review. Okay, again, during this disaster. This is COVID time. Okay, Another review article. So write so many review articles. So on this antibody drug conjugate. So we talk about different type of antibody, FDA approved antibody drug conjugate. You see that right now it's even 16 to 17 right now for breast cancers, and these drugs are very powerful and very expensive. Okay, very expensive. Okay, yeah, many countries cannot afford this drug. Okay. They use special conjugation technology. We're going to go through that, and then billions of dollars. If one drug gets approved in a small country like Malaysia, for instance, maybe you can support a big chunk of the economy. Okay, so it's not easy. So there are two. This technology right now is currently used a lot, using melanin amide that selectively wrap the tire group on the antibody. This is the technology right now available in the market. Why is this technology? Because it's highly selective towards sulfur, tire group cysteine, right? And also this is actually patent-free. It's not protected by patent. So a lot of people use that in the industry. Okay? Our technology is this technology, the arylic amide. And we found that actually it also works very well. Okay? You can compete with this one here. We have our own patent. Okay? And actually, Raj, I associate that things on the recorder. Okay? So Raj actually was a former text editor, associate editor, very harsh. Okay? By the way, he actually used our technology. Something I don't know, so that's why I don't know. So actually, editors are very harsh. Okay? So he used our linker and compared with all the linker, but not on sulfur, he actually wrapped selenium drug. Okay? And he found that our linker product is the most stable among all the existing linker technology in the market, or in the literature or whatever. Okay? So it's not stable by me, people stable. Stable means what? Stable means that during circulation, before you go to the cancer cell, it's not released. If it's prematurely released, it can cause a lot of side effects. So that's why you need to only go into the cancer cell and then release, not release, and oh, I got a lot of side effects. Okay? So we compare our linker with the one in the market, okay, using tire right now. It's just a conjugation product. And we found that ours are stable. And the blood plasma stability, we've done it, is stable. Okay? And then ours have no isomer, our product is cleaner, easy to make. Okay? So we believe that our technology, I said that about 10 years ago, I believe my technology is better than this one. 10 years ago, move very little. Because my group doesn't work on antibodies. We just start to work on antibody. My students see antibody, they shake. Okay? So, like me also, I shake. Okay? So you see protein, I shake so long until finally you go in. Take a while. Like material science right now, I'm looking at Skype, so I need to talk to the CCO. So I'm shake also in the beginning. But once you go in, a good thing about NT right now, we have many expert professors in many areas. So I used to talk to people everywhere I go. Okay, I don't mind, ask them. I want to CCO. So yeah, I stopped for a while because nobody now come back again. So in this arylic amide linker right now, we make a lot of ADC right now, hopefully soon, and we're going to do a mouse study. And if the result is good, maybe I become a big teacher, retire more peacefully. Yeah? Because all professors are very poor, so I see people a lot. Yeah? So another thing that problem with antibody drug conjugate is that how do you control the ratio of the antibody and the payload? And it's known that the payload and the antibody, the best ratio is 4:1. That gives the best effect. But there are about 16, there are 8 tire group on the antibody. So it's very difficult to control 4:1. So this is called antibody drug ratio. Okay? So what we do is that we design the conjugation technology that combine the 2 sulfur group in one shot. So you got 8, you can only 4, alright? So you got 2 technology right now, they can combine the 2 tire in one shot. So we can control the DAR ratio right now, the payload to the antibody. Next thing, antibody has other functional group, not just tire. Another important molecule is the lysine, amine. So next thing we wanted to find is, can we design a new method to just do conjugation on the amine group and not touching the tire group? Wow, more difficult. No? Tire is more active at times than compared to nitrogen. So can you do that? Okay. So we also want to actually introduce additional handle into the linker of the ADC. You have extra link handle, hand. So maybe there are 2 hands right now. One hand captured the antibody, one captured the payload. Can you have another hand that can capture maybe some sort of color compound? So the molecule going, you can actually also monitor it. So can you introduce additional handle, like silicon or boron, into the drug? So So I can cut the story short. So we decided to design using this triple bond aldehyde with a functional group here. We use boron. When we put boron, we found that you only react with the amine group selectively. It doesn't touch the chiral group. This paper just accepted science advance. Wow, it took me a long time. Because it's a multidisciplinary area. You've got referee from biology, referee from drug, referee from organic. Wow, they ask different questions. Instead of drug stability in the body, how is it? Wow, don't know what to do. Not at the door and ask people for help. Everywhere I go around asking for help. So when you do multidisciplinary, like I say, 3 key points in the paper, you require different discipline. And you need to learn or you work with people. Okay? In this paper, you need calculation. How do you want to do calculation? You want biology testing. You want drug thing. Organic is easy. We can answer all the questions on organic. Okay? But finally, after 4 times, just accepted this. And this paper, using silicon here, interestingly, the silicon will only get higher. With boron only nitrogen. This paper right now we just completed 2 papers, one from China collaboration, one in Singapore. Okay? A different type of approach using silicon. And silicon is interesting because when you introduce silicon into the linker, you're actually bridging inorganic with other disciplines. Silicon is an inorganic molecule. You can bind silicon on the surface, okay, on glass, on silicate. Sorry. So this paper here, since that's accepted, so we look at this thing here, you actually can react with this type of drug. And very interesting, we selectively only react with this linear amine, but not with the branch amine. So we just started another new project on insulin bioconjugation. Insulin got 3 different amine groups. One linear amine, one branch amine, and one electron group amine. So you want to find a conjugation technology selectively react with different amine on the insulin. Current method, they use enzyme to cleave it, okay? Okay, so cut the story short. So we do enzyme protein, and this one 7 lysine, all got conjugated. This one got 11, all got conjugated. It's just not mentioned, we only select the branch one doesn't work, but work only with the linear amine, so we can control different type of amino group. So now we also started to look into fluorine into the linker. And there are many other projects I won't go through, so I'll stop here. So I'll just summarize. The first part will come a toolbox of different reactions, improved methods. The second part will go for maybe like use-based inspired type to come up with technology. So we have a CC bond formation in water, catalyst spring. We use for protein. The first big project we started, I think 2010, we found the first paper. And then we finally found a thyro conjugation technology. They believe it's one of the best right now in the market. We hope you can use it. There are many people use it. A group in New Zealand is using our technology. Okay, US also using our technology. It's actually very slow because this is a biology project. Okay, very selective, only react the thyro. And then we have reactions that doesn't require any organic solvent, totally green, ideal green processes. And then by putting FG group here like boron right now, we can do conjugation on amine. By putting silicon, we can do only thyro. So for thyro conjugation, to tell the truth, we have already got 4 generations. And now we have published the first generation, the second generation, we have other generation coming up. And right now we have another 2 generations coming up. We have Zhengguo that's working on that. Another more interesting amine conjugation technology. Okay, I won't go through that. I need to thank my colleagues. Their names are too many students, so I didn't put their names. Maybe there are hundreds of them. Okay? I don't know how many already right now. So thanks Sim Bengkai also for coming and collaborating in the first project on the system bioconjugation. We have quite a lot. Thomas Keller, I mentioned, a protein project that we started to work. I think it's important to get good collaborators for different type of projects. Okay? And then CPH and Zhenghua is here will work on the water-based reactions. I need to thank again my student. Very small group now in Singapore is growing. I'm recruiting 3 more postdocs. And you can please welcome. I'm restarting my group chat Singapore. Okay? Group chat this 2 years ago. It was very small, now it's time to grow. Hopefully grow. Okay? Thank you, and thank all of you for your attention. Thank you very much. Sorry about that.
Prof Loh for the very inspiring talk. So it's time for questions. Anyone want to start off? We have much to learn from Prof Loh. Any questions for Prof Loh? Yes. Anton?
Hi, very nice talk. your linker does not follow, so that is safer. But when you go to the target cell, does it have to follow or it doesn't?
You have another fragment that can put as a release fragment. So all the linker has only one part there, and then there's another part for release. The release is based on the enzyme that's present in the cancer cell, or based on the high acidity present in the cancer cell. That fragment is another key fragment that we're working on. We have another project working on using sonogation. So we want the drug to go into the cancer cell. We have undergrad student working on that. Then use ultrasound to shine on it, because ultrasound is the one you can go in and then break the bond and then release the drug. Not easy. We have working on that. That's another part of research, the fragment, release fragment.
Any more questions for Prof Loh? Yeah, I have one very simple, very naive question from physics is, what kind of yields do you get for your catalyst-free reactions? The best.
No, the yield, to me, I'm happy with 70%. That's why, as a chemist, we talk to us, 70% is okay, but mathematician, we 100%. Okay? So 70% I'm happy with it. So, and also depends how you actually isolate the compound. So sometimes you put 70%, but just skeptical between plus 10 and minus 10. Depending how you weigh, you make the impurities, and that's roughly about 70 to 80% is considered very good. To me, Corey is different, huh? You want 90%. Sometimes students put silica gel inside there, so that's the same as how we So 70% is okay. Yeah, usually that's okay. That's why I say you work with chemists is different from mathematician. Mathematician you buy 100%. Right or wrong, that's it.
There's a question from the online registration. So from Stephen Ho. So Stephen asks, I would like to understand how research at CBC is done to better advise my students who are considering a research pathway.
Research, you have to go, that's why we design an undergraduate research project. I designed that. So we have two paths for students when I started this department, okay? You can tell me how we design all the courses, okay? First is the honors project for those who want to do research as a career, and the other one they wanted to do outside as a career, we go to industrial attachment. So that's very clear. So when you go out as to work in the industry, go for industrial attachment. So to start research, first of all, you have to start from year 1 to year 2. I took a lot of year 1 students. And then you go to the lab and see whether you love the research environment, first of all. Obviously, it also depends on the supervisor. So my group is I don't talk to an undergraduate unless you can't talk to me because I don't want to give you the pressure. So if you train one semester in my group, for example, in organic, say, oh, organic is not my choice, okay? Then you move to another group the next semester. Maybe you do the inorganic group, or maybe food, or whatever. After you reach maybe year 3, you say, oh, maybe I like this area of research. I want to do a PhD with it. Then you find an honors project student professor that can do a good honors project. They can get you to the top institute, not just NTU in the world. You just want student going to Princeton, my group, okay? Not student, actually work like that for a while. Esther, actually, so student at Princeton. So everything can be designed, but it requires hard work. Because I have 3 many students to Harvard, about 5 right now, I think. So can be trained by a lot of hard work. The boss, you have to talk to the boss regularly. You have to find the correct, I'm not saying I'm good, you must find the correct boss. The people know your boss will write the recognition letter. Because I know professors in Harvard, I know them, because maybe I know some of us do their my thesis exam. So we write to them, when we write email to them, they will throw inside a trash can. The first time I tell students to do is that Professor Loh sent his regards to you in the email title. Then they will open the email and just read through your CV, or else you won't go to the trash can. So we teach you how you want to apply. But not people can't see me because I didn't teach year 1, year 2, year 3 for many, many years. So a lot of students don't even know me, think that I'm really not doing research. Because there are also rumors saying that Prof Loh never do research anymore. A researcher will never stop doing research, to be fair. Never. Even I retire, we'll still think of research. Okay? So research is always in our core thing, and it cannot go away. Every day we're thinking of research. Every day I think people don't know me or know. I wake up early in the morning usually, I write paper, I read paper, okay? I talk to them. Sometimes I talk until 2 a.m. Okay? So we need to discuss. And if you think you love research, go for it. And can be planned one. But you must find a professor to plan for you. Not easy. So the one that, just I told you, went to Harvard and then I was a professor in the NUS, it's a chemist. His plan was planned. Because I was the leader of the chemistry Olympiad team at the time, I took him to, then I was voted. So they came back. Most of them would not do chemistry. go to medical school. Yeah, I told him, if you do chemistry, you have a good life. So he finished his bachelor in 3 years, and then he went to Harvard, come back, he got tenure. I think he had a good life. Once you get tenure in Singapore, very good life. You close the door, nobody bothers you. Nobody dares to go in. Yeah, so that's that. Any guys, any more questions?
Okay, any more questions from Professor Loh? Maybe for our students and young postdocs here, because now the whole world is evolving into multidisciplinary, interdisciplinary research. May I ask you want to share your thoughts and advice for these up-and-coming students and postdocs? What is the way to approach interdisciplinary science?
I think you have to tackle problems by a single discipline anymore. You have to use different disciplines to solve the problem. But it's very tough to say, to do it. It's easy to say. Like for example, I read, let's say for example, the antibiotic control, almost like maybe 15 years before I can even do anything easily and discuss with people. You need to read a lot of people materials I'm reading perovskite. I'm still very bad, okay? So one day I go to Zhejiang. The best way to learn is to ask, listen, see. You read slower. If you go to Zhejiang and say, I want to learn perovskite, ask him, hey, Professor, can you tell me what's perovskite? Give me overall. It's faster. Maybe you got time. Then 10 minutes, you actually get a very good summary. Right? Then you go to another room and talk it out. I think Professor will talk to you on research. You go to you, come and talk to me, challenge me. Prof, your research sucks. You talk to me, some students challenge me, bro. Then after I was, show to me first and then talk. I think interdisciplinary requires a lot of reading, a lot of discussion. Now I go to biology myself. I don't study biology. I go to material science myself right now. I think the good thing about certain areas, I'm not looking down at biology, which is that certain area you do it yourself. Like organic action mechanism, very difficult to do it yourself. You need to learn. Okay? Certain things very difficult. Like material science, I think we talk about physics, very difficult. So the physics part is really a blank. Huh? I hate physics, that's why I do chemical engineering. Thinking about physics, I know physics there also. So you need to talk. Ask. And then, for example, you see a paper like Nature. Let's say a Nature paper come out, and you think that you can beat the Nature paper is very tough. But the paper is using biological approach. Then using chemical approach, the chance of beating the paper is very high. But if you're using a biological approach trying to beat the guy, it's really very tough, I'll say. Or chemistry paper that come out in Nature, and you say, I want to get a better paper than that. That was my dream last time. I put all the Nature paper into my file. I don't love Nature paper, all science paper, try to beat. Very tough. But recently I found that there's one paper using the insulin one, using a biology strategy to do the protection on the immune. And now I think I can beat them because I have a better chemical method that can beat the biology method. I think that's why your mindset will be very good. Don't get scared. See the other area you travel like, what I did last time, so travel was protein. I want to go in, scared. And you have to find the correct student also. And sometimes you don't even have facility to do it. But the good thing about distinguished professor is that I can go everywhere and ask for help. People will not deny it. I think a young professor sometimes is tougher, okay? That's a good thing about an old professor, okay? You can ask around the door. Ask. Keep asking. Okay? I think that's the key. I think that's, those who take my course, so I don't think anybody here, usually I call people challenge me, okay? And ask here.
Okay, any more questions from Professor Loh? If not, let's give him a big round of applause. Thank you for that.